Great, welcome back. In this section, we're going to be talking mainly about density altitude or high density altitude. But we really can't understand this unless we truly understand pressure altitude and temperature and how all this impacts the efficiency of an aircraft engine or drone servo motor. The first part of this session is about atmospheric temperature and density. The density of the altitude at higher altitudes is less dense than the density at lower altitudes, and this is due to the atmospheric pressure pushing down on the molecules. As the temperature increases, the molecules spread apart, become lighter, and rise. We're going to do a little bit of a physics review, and we're going to talk about the effects of temperature and pressure on molecules. Let's take an example of three very tall columns of air at three different temperatures. We have column A, B, and C. And if you notice, there are more molecules at the bottom than there are molecules at the top. And that's due to the atmospheric pressure pushing the molecules together. The differences between the columns of air in temperature are 32 degrees Fahrenheit for column A, 59 degrees Fahrenheit for column B, and 86 degrees Fahrenheit for column C. An aircraft engine will perform better at the same altitude in column A than in column B and C because there are more molecules for the propeller to work on. An aircraft engine or a drone servo motor will work better in colder temperatures at the same altitudes. Now let's take a look at how an aircraft engine will operate at different altitudes. In the first one, we have 2000 MSL. In the second one, we have 4000 MSL. And in the third, we have 8000 MSL. These are three distinctly different altitudes. And an aircraft engine, based on these altitudes, will operate differently. The lower the altitude, the better the engine will perform. That's because the propellers at lower altitudes have more molecules to push. All right, let's go through some definitions. Pressure altitude, that's a measurement. And we need to think of it this way. This is the normal or standard conditions of atmospheric pressure at any altitude. It's a baseline, it's predictable. Any deviation from this normal standard is called density altitude. Normal and standard conditions. When the conditions are standard for both altitude and temperature, pressure altitude and density altitude are the same. This means they will have the same measurement. Density altitude. It, like pressure altitude, is a measurement. It is atmospheric pressure corrected for variations from standard temperature. Density altitude implies abnormal conditions from the pressure altitude baseline. We've already discussed that. Another way to say it is a deviation from an expected pressure altitude measurement for a given altitude. Throughout this entire section, we're going to repeat a lot of material. This is because density altitude, high density altitude concepts are hard to grasp. Another approach to understanding high density altitude. High density altitude. Hey, I'm experiencing atmospheric pressure that is similar to higher altitudes. Low density altitude. I'm experiencing atmospheric pressure that is similar to lower altitudes. The point to this slide is density altitude and whether or not it's high or it's low. It means that we're at a particular altitude, but we're experiencing atmospheric pressure conditions for a higher altitude or a lower altitude than what we are currently at. Here are a few items that you need to commit to memory. Performance figures in aircraft owners' handbooks are generally based on standard atmospheric conditions beginning at sea level. So you'll see this type of thing often. Surface temperature at sea level, 59 degrees baseline, 15 degrees Celsius. Surface pressure, 29.92 inches of mercury, or 1013.2 millibars. Now's a good time to remember the METAR section. One of the 12 elements of the METAR weather report is the altimeter. It had an example of the barometric pressure or atmospheric pressure. In this case, for a METAR weather report, it would be reported as A29er2. Okay, a lot of repetition here, but we need to drive this home. This is important. For the sake of safety and the exam, you need to understand the weight of the air or the atmosphere pushes down on the molecules closer to the ground, pushing them together. Air density decreases with altitude. This is standard and is not a high density element or impact. As air density decreases from the standard pressure altitude measurement for any given altitude, density altitude increases. You need to commit that one to memory. Now remember back to a previous slide, high pressure altitude corrected for variations from standard temperature. These two sentences say the same thing. Again, for safety and the exam, you need to understand the effects of higher than standard temperatures results in increasing high density altitude condition. High density altitude reduces all aircraft performance parameters. We'll be taking a closer look at that. In this example, we have three different scenarios. We have a standard pressure and temperature in column A, and in columns B and C, we have high density altitude situations. For the engines or propellers that are the examples here, they will all be represented at 4,000 MSL. But we're going to see how these engines have to perform under high density altitude conditions. Okay. Engine C has to work harder than engine A or B, and B has to work harder than A. That's because engine B and C have to work harder to push more molecules. Let's take a look at the different temperatures, that is, column A, column B, and C, and how tightly packed the molecules are at the different altitudes. The molecules that are packed in column A at 6,000 MSL are packed as densely as 4,000 MSL for column B. And in column B, the molecules are packed as densely at 4,000 MSL as column C at 1,500 MSL. So again, the more densely packed air molecules are, the better the performance of an engine. The less packed they are, the more an engine has to work. Therefore, an engine becomes less efficient in high density altitude situations. All right, in this example, we're going to look at three different altitudes. This is carrying off the previous slide of how densely packed the air molecules are due to the high density situation. So we discovered in the previous slide that column C at 1,500 MSL, the air molecules are as densely packed as 4,000 MSL in column B and as densely packed as 6,000 MSL in column A. Let's take a look. Different altitudes, but engine performance is the same. The non-standard atmosphere, temperature and pressure at these altitudes are similar to the standard temperature and pressure at 6,000 MSL. Thus, the engine and aircraft have to perform as though it is 6,000 MSL in column A. All right, this is the last slide. Whew, man, that's a lot. This is a high density altitude example, and it comes out of the pilot handbook. I think it's pretty good. All right, let's use an example of an airport with a field elevation of 5,000 feet MSL where the standard temperature is 5 Celsius. In other words, that's the standard temperature for that altitude. Under these conditions, pressure altitude and density altitude would be the same. That is to say, there is no difference between the two measurements. If the temperature increases to 30 Celsius, the density altitude increases to 7,800 feet. That means less molecules. The engine has to work harder at the same elevation. While the airport elevation does not change, in this scenario, aircraft will have to perform as though it is at a higher elevation. All right, high density altitude, wrapped up.